Donuts are fun and all when you don't have to pay for it.
I mean, that's the exact logic that Isabel has been using on me, saying that I should get more brownie points.
Okay, but that's
Because we're the ones footing the bill, not you. Everyone's opening 3-2. Okay. Up until you hit that point in Algebra 2, if there was an x up in an exponent, if there was a variable up in exponent land, you really had no way to deal with that other than to put one half of the equation in y1, the other in y2, and go find an intersection. And then we tell you the definition of logs, which is there. Okay. If I have an exponent, I also have a log. The base of an exponent is also the base of a log. The exponent itself is the value of the log. The power, remember a power is the total value of an exponent. So like 3 to the second is 9. So 9 is the second power of 3. So the power itself is the object of the log. Okay, that is the formal definition of logs. Just like I, imaginary root, or root of a -1 imaginary number, just like that unlocked a whole bunch of other math, so did logarithms. Logarithms allowed me to start taking things in and out of exponent land. Okay, a couple of you had Spear and got to hear the really bad get in the chopper, his whole spiel about that. Yep, get down, get in the chopper. It's bad. I won't even try because my Schwarzenegger impression, I end up sounding like Austin Seals, if y'all remember him. Like, it's bad. Nope. So, no thanks. That's your formal definition, but okay, some of you may have had McCurry. I think she liked the around the world example, where it was like this to this power makes this thing. Okay. B to the y makes this thing, so you kind of like make a circle around it. Okay, I kind of like that one. But you have to have that formal definition locked down. And because everything kind of switches places in this weird rotating fashion, sometimes kids get a little cross-eyed going back and forth between exponential and logarithmic form. So if you're one of those that got a little confuzzled with that in Algebra 2, or didn't have enough time and experience with it, I know my class, we got the basics, but we never got to the equations. So just because, Snowmageddon kind of ruined things for a semester. So you got to have this written down, I don't know, throw it on a scrap sheet of paper, note card, something in front of you so that you always have that to refer back to if it's something that confused you. Okay, so that's what a logarithm is. Just like square root undoes squared, just like cubed undoes cube root, it's the inverse of exponents. And if it's the inverse, that means I swap x and y. I'd use the definition to rearrange it. And if a exponential graph normally has a horizontal asymptote at y equals 0, then a logarithmic graph will have a vertical asymptote at x equals 0. It's going to use the same powers too. So like if this is powers of 2, 1, 2, 4, 8, then the logarithmic graph is going to use those same things on its side, a lot like a square root has the same perfect square steps as a parabola. 1, 2, 4, 8. Okay? So it's going to use the same powers, the same values, it's just they're on their side. And now instead of horizontal asymptote, we got vertical. Because it's a vertical asymptote, remind me, vertical lines have what kind of equations? X equals number. And now we're talking about x equals number, x is domain. So if there is a vertical asymptote at 0, and then it can get translated left and right, that means the domain of logs is special. You all remember, what the Sam hell? No. I have to put up with that with Max all of third hour. No. Jensen says that all the time. No, he's a good guy. He's a little goofball.
We're a little goofball, and look at what happened.
Yeah.
What is that?
All right. Yeah. Y'all remember your commandments of domain, right? Mathocles comes down from the hill and says, number 1, thou shalt not. Divide by 0. Number 2, thou shalt not. Even root of negative numbers. Do you remember number 3? The log one. Yes. Thou shalt not. Thou shalt not log of a non-positive. Specifically, it says non-positive, not negative. What kinds of things are not positive? 0 and negatives. So you can't take log of a 0. Everyone find log button on your calculator. And I want you to see what it looks like because y'all get that quit screen, that error screen, and you just, it told me to quit, that's discouraging. Like, just hit log of 0 and see what it says. Okay? Okay, error domain, because it breaks these commandments of domain. Yes, ma'am?
Oh, no.
Okay, a good question. What if the base is negative? Take a look at the formal definition of it, and it says b is always greater than 0. Remember we said that the base of an exponent was always greater than 0 too? Because otherwise it would keep swapping negative, positive, negative, positive, negative, positive, negative, positive. Same thing would happen with a logarithm. If you had a negative base, that logarithm would keep flopping back and forth and back and forth and back and forth between the x and y axes. Okay? So b will always be a positive value. That also means that the object of the log has to be a positive value. Okay? So, by definition, easy peasy, if I'm going to evaluate this, it's asking 3 to what power made 81? Okay, so think of it like this. If I'm evaluating, I'm saying this equals x, right? This equals what number? So, I say 3 to what value makes 81? Four. Oh boy. How many times have we said this already this semester, or those of you that have been in here all year because you're in Algebra 2? You should know your squares through 20, cubes through 10, fourths through 5, as many powers of 2 and 3 as you can memorize. Off the top of your head, 4 to the 4th.
64 times 4. Is 256.
Okay. 7 to the third. 7 to the third. 343. 15 squared. 9 to the third. 729. Okay. Y'all, you got to know these. Not because I'm going to force you to memorize them, but because just like when you were first learning factoring quadratics in Algebra 1, if you knew your multiplication facts, how many of you were able to do factoring quadratics fairly easily, and you watched some of your peers guessing and checking and guessing and checking and guessing and checking 1,000 times on their calculator? Okay. Number fluency just increases the speed with which you can do things because they're familiar. All right? I hope that you can get more familiar with those numbers. When I say log of a thing, I am saying 3 to what power made 81? That's it. It's just 4. The value of this logarithm is 4 because 3 to the 4th is 81. Okay? And that definition can make some of us go a little cross-eyed. All right. 5 to what power makes square root of 5 if we don't remember rational exponents? Oof, yes. Okay, this is 5 to the 1/2, and this might lead us to one of our properties. This says 5 to what power makes this thing? So if I know that square root of 5 is 1/2, remember, exponent inside or parentheses outside, and my denominator is going to be my index. Do any of you remember that there's a property with this that says if the base and the object are the same, they cancel out? Okay. So we got to know not just our logarithmic values, not just our exponential values, but do you remember that x to the a over b is the bth root of x to the a is the bth root of bth. Okay, so you also have to remember those so that you know this is going to be a 1/2.
You sound like Michael. No. We got your donuts. Not today.
You're supposed to
Look
be
away
happy.
from the board. Look away from the board. Just walk away.
So, y'all use that definition. Here you go. Take it in pieces. Deal with the exponent, evaluate the exponent, then do 3 to that. Yep, do it that way.
So you would try to find this first and then multiply it by 3.
Well, not
Or
multiply, but
take
3
that.
to that power. Yep. So 3 to what power makes 1?
No, 0.
Okay. So that means that entire exponent is 0. Okay, what's 3 to 0? Yay.
Smart brain.
No, that's Frank.
Franklin.
No, just Frank. If you called him Franklin, he like flipped out. He would leave class. No, the kid that the board is named for.
Yeah.
He was Frank.
But was his name Frank?
Yeah.
Franklin. Did you call him Franklin? Just,
Like his parents were really mean too. I want to say his middle name was Benjamin.
Franklin
what was his last name?
I don't know, something lame like Jones.
Franklin Jones.
So, okay, you use this definition, 9 to what power makes 81, and it's just 2. But if I use that definition, this says 9 to what power makes 81. Do you remember in Algebra 2 rewriting these as 3 to the second and 3 to the fourth? Now, they happen to have the same base right now, 9. But this is something that we're going to use in a minute here to start to wiggle around things that share a base. Isn't 3 to a thing, is it 3 to a thing, means thing better equal thing, didn't we still get 2? Okay, so that's a definition thing that we can work with. Over here, a couple of you figured it out. Deal with this part first. Log base 3 of 1 is what? 0. 3 to what power makes 1? 0. Okay, take 3 to that power. What would I get? 1. Which leads to another one of those cancellation properties that if the base of a log and the object of a log are the same, cancel. If the base of an exponent and the base of a log are the same, they cancel. It's just 1. Because it was log base 3 and an exponent base 3. They just cancel. Which allows me to do some really goofy ones, like I could say pi to the log base pi of square root of 7. Square root of 7. Okay? So, those are all properties of logs. We're just kind of sprinkling them in as we go. Here they are for real. Okay? This is called the common log. That's why you all have that button on your calculator. Common log is log base 10 because our number system, most of what we work with, is base 10. It's base 10 because most of us, unless you're from Alabama, have 10 fingers. So we have a decimal system based in 10. If I say log without anything written in the base, just like if I have a radical without anything in the index, I assume this is a 2. I assume this is a 10. And if I take the log of anything, I'm asking 10 to what power makes this? So if I say log of 1, well, 10 to what power makes 1? Just like log base 3 of 1 was also 0. Okay, log base b of 1 will always be 0. Notice that they cancel because it's kind of like an invisible 1 up there in exponent town. Base and the object are the same, cancel. Base and the object are the same. Cancel. Base and the base of the exponent are the same. Cancel. But they are careful to say that x has to be greater than 0 because it's in a logarithm. Remember, thou shalt not take log of non-positive. So they have to make that, they got to have that catch to it and say, but it has to be positive. Okay? So this one's called common log. Common log is base 10. We're going to use it an awful lot because it's a button on our calculator. And then, I don't know how many of you got to this part last semester if you had Algebra 2 last semester. Natural log. Okay? If I ever have log base e of a thing, because e happens so often, it gets its own special name. Kind of like if someone is an absolute goofus in class all the time, they get their own special spot on the board. Okay? Right? They get their own special name. Well, base E happens so often that it gets its own special name, ln of x. Okay? ln, this has bothered me since I first learned about it, is natural logarithm. You're like, but it's L and then an N. Maybe the person who made it was French. Log au naturel. Okay, I don't know. But it is natural logarithm. It is just a log base E. Okay? Which means it's going to have all those same properties. This is saying a log with a base E. Well, E to the 0 still makes 1. E to the first still makes E. It has a base E, so they cancel. It has a base E, so they cancel. Okay? So it's just, it happens so often, it gets its own special name. All right? Check your calculator. Somewhere near log, you should also have ln. All right? There's a lot of applications, particularly in science, where you have to use a base E because in the natural world, things happen continuously. Think about bacteria growth. Any of you ever done the swab test where you run around with the Q-tips and you get like your phone and the doorknob and toilet seat and you bake them in the cultures? Never done those? Like, isn't in foods? You're supposed to do that in biology. Well, okay. So it's, you put it in a growth medium. It's like basic carbohydrates and stuff for bacteria to eat. In a petri dish, you take a swab with a little bit of water on it, just so it's got, absorption, and you would rub it on various surfaces. You put it on a doorknob, and then you'd stick it in the growth medium, swish it around a little bit, throw it away. And then you put all of those in an incubator. It's just basically an oven set on low to let the bacteria grow, and then you get to see the different types of colonies that grow in that petri dish. Oh, okay. Well, apparently they do it in foods, so take foods, because it is very enlightening. Okay? It is very enlightening because it turns out stuff like, have you heard things like there's more bacteria on your phone than on a toilet seat? It is true. It is very true. But you also have to take into account the severity of the bacteria. The amount of bacteria on your phone absolutely is worse. But fecal coliform bacteria that would be found on a toilet seat is bad. You don't want to ingest that. You can lick your phone. It's fine. Okay? You probably don't want to lick a toilet seat. But that's not a thing in biology?
It is.
Bio 2? Okay. Okay. So, things like that happen continuously. So you will see E a lot in science, which means natural logarithm gets used there. Physics. Anyone in physics? Physics will use logarithm, like base 10 an awful lot, because, remember scientific notation? Decimal times 10 to the thing. You're going to have a base 10, so it's very common to use the common log. It's also why you should really take PreCalc before physics. So now they're going to just go the other direction. This one, I'll start over at B. Easy peasy. Also, think about just the context here. What's the base on this? So they are going to cancel, but think about the logic behind it. 10 to what power makes 5? You are repeatedly going to multiply together tens until you get 5. You would need like part of a 10, right? Like you can't do that with just integers of 10. But it's some decimal. If I said 10 to what power makes 5? Okay, now take 10 to that power. You're going to get 5, right? If I throw a water balloon at you, what happens? Okay, I'm going to throw a water balloon at you. Like, the thing is going to happen, right? This says 10 to what power makes 5? Okay, take 10 to that power. What am I going to get? 5. It's basic logic. Now, there is proof to it, but yeah, that's why it happens. Okay. I told you before that we don't like decimals in this place because, well, not stupid. It's just fractions are superior. What place value is that 1 in? So this is 1 tens, hundreds, thousandths. 1,000 is 10 to what power? So this is 1 over 10 to the third. Doyle called it. And if it's on the denominator, we know our properties of exponents. This is log of 10 to the negative third. So if it's log of 10 to the negative third, well, the base is the same of the exponent and the log, so they just cancel. It's just negative 3. But you need to know the definition or you will not be able to do the equations for these. Okay. 10's place value? Oh, that's 10 to the third. I just wrote it bad. Sorry. Are things in the real world just given to you the way you want all the time?
Yes.
I'm sorry. Hold on. We'll sit down and let us process that privilege. So, log of 26. Can I repeatedly multiply together tens to make 26? It's going to be some funky decimal, so grab your calculator, press the button. Okay, you're just going to have to press the button. Oh, my calculator's on the other screen. 3. I am still a fan of 3 places, so we're just going to say is approximately how much? Okay. But please make sure that you say approximately, not equals. Okay. Now, depending on the model of calculator, sometimes as you're doing these logarithms, it might spit it out as a fraction. If it's good enough, it might be able to split it out as a fraction. And that comes from the different properties that we learn in section 3.3. Okay, what about D? No. Like, literally, that's the answer. No, you can't do it. I can't do the log of a non-positive. It breaks domain. All right. Get him. Okay.
Don't let it trick you, Jacob. Hold on. Hold on.
Because a negative exponent just puts something on denominator.
have negative 0.
There could never be a negative 0.
Can you do that?
No.
But why would you have
It's
negative
just 0.
To make you ask that exact question. What's a negative 0?
It can't be 0 anyway.
Nothing.
0. A positive 0 and a negative 0 are just 0.
Yeah, I got a thermometer that pulls janky stuff like that.
I don't have to go back. I hated it. I was too shy to talk. And I had speech problems. My brother has speech problems.
Same. I got that Morpheus gap in my teeth, so I had a bad lisp.
So I couldn't say half the right sound.
So, contestant 1, 10,000 is 10 to the 4th. So 10 to what power makes 10 to the 4th? Just 4. 10 to some power makes 3. Okay, take 10 to that power. 3. Log of a non-positive is illegal. It's just to make you think.
It's stupid.
And then 0.081 or 81 thousandths. I could simplify it. If you remember, log of 81 thousandths is log of 81 minus log of 1,000. Okay. But I still can't repeatedly multiply together tens to make 81. So I'm just going to have to jam it in my calculator. So you get approximately, how much? I heard 092 and 068. Okay. So yeah, section 3 is just those properties again. I know that's my class. We got through properties. We started equations, but didn't get too far into them. We kind of had to triage at the end there. Losing a week at the end of the semester is rough. Okay, now they're going to switch over to LN. Natural log doesn't change the properties. The properties are still the same. This is a base E and a base E. So e to what power makes e to this power? 0.73. E to some power is going to make 6. Okay, take e to that power. I'm just going to get 6. All right, ln is just log base e. So it's still going to follow all the same properties, all the same rules as any other log, like thou shalt not log any base of a non-positive. No, can't do it. And if I say e to what power makes 4, well, I'm repeatedly going to multiply together an irrational number approximately 2.72 until I get 4. Go press the button. The ln of 4. Okay? So if you can get a integer or rational value, great. They're not always going to work out that way. Sometimes you just got to let the calculator do it for you. In the ancient days, this is even before me, but I remember working with textbooks this old. The textbooks would have in the back of them tables, just charts and charts and charts full of numbers, where you didn't have a calculator to go find what the cosine of 38.925 degrees was. You would go look up 38 into the tenths, 9 into the hundredths, 25 into the, and you would go find that decimal equivalent of it because someone went through and did all of those by hand and then recorded it in a table. They did the same with logarithms. Calculators are good. Okay. So, same thing, it's just now we're dealing with ln. Go. Now, what I would caution you about is, yeah, calculator's got the ln button. It's got an E button. You can just press those buttons every time. You got to know the definition and how it got there. Particularly because when it comes time for quizzes, I say you must show some form of work to demonstrate the knowledge to receive credit. You could absolutely use the calculator to check that. But don't just rely on the calculator to do everything for you. Also, the calculators, sometimes they're going to give you some nasty decimal answer when it could have been written as a rational number. It could have been written as a expression value with E in it. Yes, ma'am.
So is there a way you would bring that over?
I can put it up into exponent town, yes. It's called the power property of logs. We get to it in 3.3.
So it's ln
9 to the negative first, or ln of 1/9.
Okay.
ln of 1/9 and negative ln of 9 are going to be the same value. Okay. Is anyone still going? They're fairly quick. Okay, contestant 1. Nothing to do about it other than jam it in a calculator. E to something makes this. Now, since E is about 2.72, and since 3 to the third makes 27, I can ballpark it that this is going to be 3 point something. But other than that, I got nothing. I need that calculator to do it for me. 3 point what? Okay. E to some power makes 4. Okay, take e to that power. Just 4. Rewrite as the ln of e to the negative third. Now all of a sudden you got the base of the exponent and base of the log are the same, so cancel down. Negative 3. Am I allowed to do 4D? Because it's got a negative log. It's not the object of the log that's negative. Okay? Negatives out front are perfectly fine. So I'm going to still have to jam that in my calculator because I don't know what e to something makes exactly 9. So all right. So all of this should be review from Algebra 2. Maybe some of us didn't get the natural log business, but you see it's the same thing. Okay. Same character, new skin. I want you to just take a look at all of these and just tell me, are there any of them that look weird? Like, yeah, this is 8, this is 10, this is 3, that's negative 2. I know all of these. What is that? Any of them weird? Number 8. Okay. Don't overthink it. It's still a base e, right? So e to some power makes this expression. Take e to that power. I'm going to get that expression. Okay? Yeah. Remember, answers can have variables in them. Any of the other ones weird? 5. It's a 9. It's just a really, really pixelated, blurry 9. 4. Okay. You take it in stages. E to what power makes e to the 5th? So it becomes 2 times 5. The coefficient in front of it. Now, okay, Holly's remembering some of our properties here. Absolutely, you can simplify this by coefficients can become exponents, exponents can become coefficients. And do you remember what we do with an exponent to an exponent? Multiply them. So that becomes the ln of e to the 10th. Well, it still cancels and makes 10. And as we get into section 3 and 4, this is what we're going to start seeing is because logarithms are the inverse of exponents, and exponents are repeated multiplication, and multiplication is commutative. Remember, the order I do it in doesn't matter. 3 times 5 is 5 times 3. Because of that commutative property, you're going to find out that there's like 9 different ways to simplify it. They're all going to get to the same place. If I ask everyone in here, how do you get from here to, I don't know, how do you get from here to Dairy Queen? Okay. Some of us are going to use the main drag. Some of us are going to go all the way around on the interstate. Some of us are going to say, I hate the one in town. And they're going to drive north to Bell. I just said Dairy Queen. Okay. Don't do the one in Bell. It's nasty. So just know that there are going to be different ways to do these problems. I might do it one way. You ask, hey, is this legal? I'll run through it and I'll show you why it is. Okay? As long as you're following the rules of the road, you're going to get there. Okay, the graphs of them. Like I said, this is the inverse of 3 to the x. Real quick, you don't have to write this part, but I'll show you the proof for it. This currently says log base 3 of x is y. To make an inverse, what do? We swap x and y, right? So first, I'll do this. Log base 3 of y is x, and then use the definition, getting y is 3 to the x. Okay, so this is the inverse of 3 to the x. Well, if 3 to the x looks like 3 to the 0, 3 to the first, 3 to the second, 3 to the negative first is 1/3, 3 to the negative second is 1/9. If that's what 3 to the x looks like, then it's, I said you don't need to write that part. I was just showing you that this is the inverse. Then, if that's 3 to the x, its evil twin, the inverse, if there was a horizontal asymptote at y equals 0, now there's going to be a vertical asymptote at x equals 0. If there was a point 0, 1, now there's a point 1, 0. If there was a point 1, 3, now there's a point 3, 1. 2, 9 becomes 9, 2. Negative 1 1/3 becomes 1/3 negative 1. Negative 2 1/9 becomes 1/9 negative 2. You see that it's the exact same thing, the exact same numbers. They're all just tossed on their side. Okay? It is still 3 to the first, 3 to the second, 3 to the third, 3 to the... It's still all the powers of 3, it's just they're on their side. What I'm going to tell you is to be careful, please be careful. Show your asymptote. Got to really enunciate that in a room full of teenagers. Show your whole asymptote. Okay? Because, here, reset. Come on, Frank, hurry up. I want you to see what the graph looks like. Ruh-roh, Raggy. When I go look at the graph, it's not going to show me the entire graph. Why not? Calculator kind of dumb and it doesn't have enough pixels. Remember that this graph is going to continue going downward along this vertical asymptote, and the calculator says I'm not allowed to show anything at 0. So it's just not going to show anything, and it's too close to 0 for it to tell the difference. You got to be smarter. When you make the graph, you absolutely have to show me that it continues all the way down. Also, another reason to put that asymptote on there is because I will see kids year after year after year, they'll go find like a point here, a point here, a point here, a point here, plotting by table, and then they'll do this. You will get points off. And even though I'm making all of these declarations right now and saying, please be careful, don't do this, someone in here is going to do it on their test. Guarantee it. Okay? Please show the asymptote to keep yourself from making that mistake. If you run an older calculator, the TI-83s, they'll actually show you that asymptote on there. It's a problem with some graphs, but it's helpful for these. Oh, we got to do the stuff. 3 to the 0, 3 to the first, 3 to the second. Domain, range, x-intercept, y-intercept. What else we got? Continuity, symmetry, increase, decrease, limit as x approaches a thing, limit as x approaches another thing. All right. Talk to me, Goose. What is x-intercept?
Sorry, not
One. Positive one.
Just one. Okay.
Oh, wait, you put that in the domain.
What? Y-intercept. No. Okay, I wanted to do x and y intercepts before domain range because that kind of matters. What is the domain? 0 to infinity, parenthesis or bracket. Thou shalt not, log of a non-positive, 0 ain't allowed in this party. Range. Okay, it is all real numbers. Now, this is gonna, because it's the inverse of exponential, it's gonna take a very, very, very long time to get up here. A really long time. Thankfully, it has infinity to do it. Okay, continuity. How did we say this? It is continuous, but you have to say where. So don't just say continuous, say it's continuous from 0 to infinity, because everywhere 0 to negative infinity, it's not continuous, it doesn't exist. There is no symmetry to this. As I go left to right, where is it going up, increasing? Not 1 to infinity. 0, right? If I was at like 0.00001 and then 0.4, it went up. So 0 to infinity. Decrease, no. The right end behavior is easy. As we go to infinity, y's are also going to infinity. Do you remember how to do the left end behavior of this? As we approach 0 from the positive side, where are my y's going? Down to negative infinity. And if you're not sure about how to do that, basically put a coordinate at both ends of your domain. This is approximately 0, negative infinity. This is approximately infinity, infinity. So that informs what your limit's going to be. As I approach 0, my limit is negative infinity. Okay? So, all that same stuff, boop, boop, boop. See, I get to cheat and just move over. All right. There's no translations left and right. So I'll still have my vertical asymptote at 0. But now instead of using powers of a whole number like 3, it's powers of 1/2. What's 1/2 to the 0? Oh no! What's 1/2 to the first? A half. 1/2 to the second. I heard you. I'm waiting for someone else. 1/4, right? And then 1/8, and then 1/16, and so on. So it's going to be creeping along the asymptote, and then Remember, just like 1/2 to the x, it flipped it. A base of 1/2 is also going to flip this. 1/2 to the negative first is 2 to the first. To the negative second is 4. To the negative third is 8. To the negative fourth is 16, and so on and so on. So think of it like a vertical reflection. Okay? Again, if I look at this on my calculator screen, it's not going to show me that entire graph. It'll show me until, it'll show from like x is 1/2 onward, but after that it's too close to the asymptote, it's just going to give up. So now that I got my graph, oh, suppose I should say this for our TI-84 users. How do I even put a log base 1/2 in here? Okay, log base is in math. Over to number, one of the types of numbers that I can do is, or wait, no, it was just math, right? There we go, log base. The other one is, if you're on an 84 plus or better, alpha window brings up the most commonly used functions. And one of them is log of another base. So I'll put a 1/2 down there, go to x, graph of a, and again, see it only shows part of it. We got to be smarter. All right, now that I got all that stuff, or I got the graph, tell me all the stuff about it. Domain. Still 0 to infinity. Range. Ah, crap, it's right there on that page. I thought it was on the next page. Yeah, same stuff, right? It's going to be all reals. Your x-intercept is still 1. Your y-intercept doesn't happen. It's continuous, 0 to infinity. No symmetry. Not increasing this time. Decreasing the entire domain. As we go all the way out to positive infinity on the x, the y's head down to negative infinity. As I approach 0 from the right, my y's go all the way up to positive infinity. I thought I printed all of these so that that was always on the next page, not right below it. Oops. Oops! So, the analysis part of it, I think we're all good with. We've kind of beaten the graph analysis to death. I'm happy with that. I want to make sure that you can graph them. So don't worry about the don't worry about writing out all of the analysis stuff. I just want you to graph these two. And I want you to try doing it by powers and then confirm with the calculator. Don't just graph by points from a calculator. I want you to know your powers, be able to graph by powers. Some of the bases and exponents in this chapter get really tiny. That is a 1/3 on part B. I just want you to be able to graph it. Graph using powers and points instead of just the calculator. Looks like it doesn't take too long because I just saw like 5 phones simultaneously hit the hand. You should have powers of 2 are 1, 2, 4, and 8. Powers of 1/3 are just a reflection of powers of 3. So 1, 3, and 9 curl along the asymptote, take off. And until you get used to that asymptote and always following along it, I would strongly recommend showing that asymptote. I see a couple of you doing the asymptote in just like a highlighter or something, like a different color. So you understand that that's not a part of the graph itself, it's just a feature. I like that. That's big brain. Ha! No! We got like 25 minutes left. No! All right. Yes, all the stuff, all the analysis stuff of it is right there. I said I think we're good with that. Transformations. If you need to write it in here, maybe this is a good space to write it. Logs are going to use all that same stuff that we've been doing. Y is log of some base, or I could replace this with ln, right? Because it's special. It's still got all the same old usual suspects. A. Oh wait, I can't say B anymore because B is used as my base. I'll just use C, I guess. C, H, and K. They're all going to do the same stuff they were doing before. A, vertical dilation, vertical reflection. C, be careful, it has to be separated from the x minus h. Has horizontal dilations and horizontal reflections. H, horizontal translation, both C and H are bass-ackwards. If this says -5, I go right 5. If this says 5, I have 1/5 reciprocal. And K is my vertical translation. Yep, it's always by here. If C is less than 1, there's a stretch by 1 over C. If C is greater than 1, there's a compression by 1 over C. It's always a reciprocal, bass-ackwards. So like if there's a 5 there, think about, or how many times have we seen say I got a 2 here. I'm saving X amount of money for my, my goal. I'm saving up for that car that we found out is way too expensive. What happens if I double my input? Does my goal get further away, a stretch, or closer, a compression? No, something less than 1 is like 1/3. The reciprocal of that is 3. Greater than 1, the reciprocal is 1/3. So it's always the reciprocal when you're dealing with the horizontal stretches and compressions. We didn't deal with horizontal dilations very much in Algebra 2. I don't know if the new curriculum does it at all. The old curriculum barely touched it. But, well, it's because it can be, that C value or B in any of our other functions, it can usually be turned into an A value. Like if I said y is 4x minus 8 squared, I would turn that into 4x minus 2, the quantity squared. And now 4 squared is 16. So I'd turn that into this. Like, those values can be turned into A values. That's why we didn't see them very often in Algebra 2. So all of the transformation stuff is the same. So if I see something like this guy, this tells me there's a vertical reflection. This is not grouped in with X, so it tells me it's a vertical translation down 5. I'm still going to have my vertical asymptote. It's just that initial point that's normally at 1, 0. I'm going to move it down 5. 1, 2, 3, 4, 5. And then the powers of 10 that I normally use, I'm going to reflect them. So 10 to the first, 10 to the negative first. Okay, I move that initial point down 5, reflect it. Oh, and it's base 10 because common log. So I'll use powers of 10. Okay, so you tell me the transformations, you graph it. We have beat transformations to death. Let's do that one, and ooh, they're all LNs. I like that. Let's do the C's. Oh, okay. Back that math up. Okay.
How would you do that? Put it simpler? Is it exponential form? Because it's easier to work with?
No. It's a log. Okay. Normal log. Normal y equals log x has a base 10. So I use powers of 10. Green. 10 to the 0 is 1. 10 to the first is 10. 10 to the negative first is a 10th. So here is OG, mathematical daddy. So I'm going to take that, and just like, remember on a cubic, you have the inflection point in the middle? Just like with a parabola, you got the vertex, and that's the thing that we always move with translations. I'm going to take this point and move it down 5. And then instead of going up and to the right, I'm going to go down and to the right because of the reflection. So instead of like here, I go up 1 and over 10, instead I'll go down 1 and over 10. Instead of going down 1 and over a 10th, I'll go up 1 and over a 10th. Yes. And you're going to see the bigger the base of that logarithm, the more it looks like instead of a curve out to the right, it's almost going to look like just a big L. Big L. It's just going to take off to the right real fast. Okay, the C's. Let's try the C's. Oh, that didn't do anything. I would always, always, always do my horizontal translations first so I can get my asymptote on there.
What? Like 20 something? There's like 7 different people with that person that I know. Or the 20 people.
Okay, starting with yellow is good old log of x. Do you see how the translation moves it left 2? All of your powers are going to be from that asymptote. So I'm going to move 1 away from asymptote, 10 away from asymptote, 100 away from asymptote. Cool? This isn't the final answer. What is this? Vertical stretch. So what I'm going to do is take this and move it 3 times higher. I'm going to take this and move it 3 times lower. So my points are negative almost 2, 1 and 9/10, negative 3, negative 1, 0, and 3, 8. Because now the vertical distance between these power values is 3 instead of 1. It's 3 times taller. Your graph will be vertically stretched taller. Okay, normal log of x takes off very sharply. This just got bent upwards. Okay, stretched up. And then I would say vertical stretch or dilation by 3, a horizontal translation left 2. Okay. So vertical stretch just stretches the vertical spacing between those. Remember when we did our greatest integers? Like this? If that had a vertical stretch to it, it just made, screw you, it made this one come up here instead, made this one come up here instead. It made the vertical spacing between them bigger. The same thing is happening here with the logs. The vertical spacing gets bigger. Okay. Remember we said E was about 2.72. E squared was about 7.29. Double check me on that, like E squared. I always remembered 729 because 9 cubed. 3.8. Samsonite, way off. Well, 7 and some change, right? There. So if normal ln of x has vertical asymptote of 0, anything to the 0 power is 1. E to the first was 2.7-ish. E to the second was 3, 4, 5, 6, 7, and change. E to the negative first will be 1 over E or tiny decimal. Okay. How do I change this with this guy? Horizontal translation left 4. So I'll take this whole, I'll take my asymptote and move it 1, 2, 3, 4. So that means my initial point should start 1 to the right of the asymptote. Should. But then they tell me a vertical translation up, that's a 3. So this point here will go up 3, and then I'll start my powers of E. E to the 0, 1. So 1 away from the asymptote. E to the first was 2.72-ish, so I'm going to go 1, 2.7-ish away from the asymptote. E to the second was 7-ish, so I'm going to go 1, 2, 3, 4, 5, 6, 7-ish away from the asymptote. Still have itty-bitty fraction. Connect the dots. Okay? Always do your horizontal translation first so that you can get your asymptote on there. You can. You better know how to do this because We're also going to work in reverse. I'm going to give you the graph. You have to tell me the equation. And if you don't recognize powers, you're going to be toast. Let me double check the examples here. Yeah. Okay, so let's say, go over and use the A spot. What if I just gave you this graph? Nope, completely missed. Tell me the equation. Okay, how do we do the equation from that? So if you want the points, just because that can be really hard, this is 1, 2, 3, 4, 5, 6, 7. This is 1, 2, 3, 4, 5, 6. This one here is at -6, -2. This is at -4, -4. This is at 2, -6. The other one is at a decimal of some sort. Okay. Plot that, and then to determine an equation from it, I have to know what transformations do. So I know y equals, I'll leave a spot for a. I've got log of some base. Sullivan's not going to be mean yet and do a horizontal change. You have to fill in a, whatever your base is, whatever your h and k are. So, what kind of things could you tell me? Do you know where your asymptote is? -7. So, right here, if I went left 7, then I know this has to be +7. Okay, I've got that much. Next up, check those dots and what powers they represent. This goes right 1, goes right 3, goes right 9. So if it goes right 1, 3, 9, what kind of powers am I dealing with? Base 3. So I can put log base 3 in. Okay? Normally, anything to the 0 power equals 1, that's my initial point, right? Like the inflection point in a cubic or the vertex on a parabola. Something to the 0 power is 1. This is normally my first point. Isn't it normally on the x-axis? it got moved down 2. So that tells me I also have a vertical translation down 2. And then it does move down 2, but then there's a spacing between each set of points by 2. So I also have a vertical stretch of 2. Both. And then, because my because my logarithm goes downward instead of upward, I know that's a -2. Boy, that is terrible. There you go. Okay. So we got to work forwards and backwards with these. We have done transformations. It's just how familiar we are with logs. Okay, so we're definitely getting graph practice tonight. The last thing, they want us to rearrange the numbers and the formulas a little bit. I'm going to tell you honestly, every bit of the word problems that you will see here are blah, 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 shove it in your calculator. It's just a word problem that has a log in it. You're just going to shove it in your calculator and evaluate. Okay, I'm not concerned about them. So, yeah, I was wondering if this would be a little bit iffy given our how many of us had Algebra 2 last semester. So, that's it. Well, then you have the other problem of it's been a year or a year and a half since you've done this.
Yep.
So, tomorrow is properties. If you remember expanding and condensing log expressions, that's tomorrow. Everyone who did not get your ransom already, get your ransom.